So, let's begin. So this is the next bit, which is on energy of a system. Sorry, it had to pop out because there was an issue about I have a corrupted file on this. So when I try to do a PDF version from my Word file, I keep having problems, and I have gone through that thing and took out every image and basically recut and repasted, and it seems like it works. And then the second time I try to get a PDF from it, it's corrupted. So I think I'm going to have to write the entire file again, which is a bit of a pain. But so I'd forgotten that I hadn't made this into a PowerPoint, so I just did that. So we're changing a bit. We're going to talk about energy, and the key thing about energy is that energy is a kind of confusing thing. Energy was not kind of addressed seriously by the scientific community until the 1850s. Now, you think about the Industrial Revolution was really beginning by then. So 1850s is quite late. And they did not really get what was going on. They'd made some rudimentary engines, and they weren't making progress particularly. And then they started realizing we got to get this thing called energy sorted out. They thought it was a kind of different thing from mechanics. They thought that anything to do with heat was kind of like weird and different. They had this caloric fluid theory. And it worked to some extent, but not particularly well. And then along came Joule, who said heat is another form of, the stuff you have when you do work. And so they started realizing that there's a mechanical equivalence of heat. We can do work and create heat. We can, if we're clever, use heat to create work. And we can keep track of it via this thing called energy. So energy is what you put in an object. Work is one of the ways you get it in. There's two ways you can get energy into a block. You can do work on the block, or you can apply thermal energy to the block. You can heat it up. So we're going to focus on this bit, on the first aspect of it. Is we're going to talk about work. We're going to talk about doing work on objects. That then brings us towards storing energy in objects. And then later on we'll talk about the thermal manifestation of this. So what we talk about here is work and energy, a scalar quantities. They're not vectors. And they have the same units, which is the joule, named after Joule. And work is performed by the displacement of a force. We'll spend a fair amount of time on that because it's very specific. Work can be stored. Work can be used to store energy in an object. We do work on an object, and therefore it is changed. It has some manifestation of that activity. Could be it's going faster. Could be it's higher in some kind of force field. Could be it's squishing a spring up. So there's some manifestation of the energy. And energy can be defined as the ability to perform work. That's a kind of catch-all definition. And common types of stored energy are, we're going to talk about kinetic energy, that's the energy in motion, gravitational potential energy, that's the energy of location in a gravity field, and spring potential energy, which is the energy of location in a spring field. So, okay, and let's make a start. So let's talk about work. Work is done by a force. It's not done by an object. I don't do work. My lifting force does work, or my pushing force does work. Now, in colloquial terms, we'll talk about objects doing work, but we really mean a force that's doing the work. And so we have to make a force. We have to take a force, the size of the force, and we have to multiply it by the distance, the displacement that the force moves through. Now, if the force is acting on an object, it's the same as what the object moves through. But we have to have the force vector in line with the displacement vector. It's not any old force and any old direction. It is a force vector in line with the displacement vector. And if they're not in line, you take the component of one and multiply it by the other. So in this case, I have a force which is not in line with the displacement. The displacement vector is that guy. There's my force vector. There's my displacement vector. They're not in line with each other. So I can take the magnitude of that force and convert it into a component that's in line with the displacement. So I go F cosine theta multiplied by d. So F cosine theta multiplied by d. So it's the component of the force in line with the displacement. Or I could, if I wanted to, take the component of the displacement in line with the force. And I could have said, well, it's F times d cosine theta. Or actually, I could have took the component of the force and the component of the displacement along a common axis. It'll also work. But they've got to be along the same line. So we say work is the displacement of a force through a distance. Work is done by the force. Work is a scalar quantity. Work is measured in joules. And if the force is perpendicular to the direction of the motion, so here's my force, and here's my displacement, and that is 90 degrees, no work is done by that force in that displacement. The force is still there, but it's not doing any work in this displacement. So that raises some issues, and the issues it raises are, if I have a box and I raise it in the air, is my lifting force doing work? You bet it is. If I lift it slowly, my lifting force is equal to the weight of the box, and I take the lifting force and multiply it by the displacement. It's in the same line, so I can do that. If I hold my box and I walk across the room, has my lifting force done any work in transporting the box? And the answer is no. But my arms get tired. That's a biological effect. We don't think about that. We don't worry about that. If I go up a ramp, this is the interesting one. If I go up a ramp, let's have a ramp. Let's say this is 3, that's 4, and this is 5 meters. And here's my lifting force. Let's say the lifting force is 10 newtons. My work is equal to 10 newtons times which of those distances? Is it 10 times 4? Or is it 10 times 5? Or is it 10 times 3? What is the work done by my lifting force? It's the force times the displacement in line with the force.
3.
So would it be 10 times 4, 10 times 5, or 10 times 3? And the answer is? You said it? 3. Because they're in line with each other. That's that. That's in line with that. 10 times 3. 30 newtons. And that picture is, I think, 30 joules. That picture is very useful because I think it crystallizes out the dilemma you've got. You've got to get the displacement in line with the force. Or the force in line with the displacement. Student pulls a 4-kilogram bag 3 meters across a level, rough floor by applying a steady force of 6 newtons at 20 degrees above the horizontal. How much work was done by her 6 Newton pulling force? Can you have a go at that, please? Let's get those brain cells going. So, think of your definition of work. And click in. give you a little bit longer. Come on, you can do it. Come on. Write down your expression for work. Look at your diagram. Work your calculator. Come on. Let's go. I'll give you until 2 minutes. Got another 30 seconds. Stop you now. That's going to be mainly A. Let's have a look. Definition of work. Work equals F times D times the cosine of the angle between them. Turns out it doesn't matter which one we take. Component of one versus the other, or the component of the other versus the one. Still going to come out to be the same thing. So work is equal to 6 times 3 times the cosine of 20. So work equals our old friend. It's going to be, what was it? 16.9 joules. Cool. 16.9. Cool. Work is a scalar, but force is a vector and displacement is a vector. When you multiply vectors together, you got two options. Either you're going to get a scalar answer or you're going to get a vector answer, and this is a scalar answer. And so we need to learn a little bit. How many people have done dot products or so-called scalar products in math? Anybody not? Anybody not done it? Okay. So let's bit of review then. So basically we have a symbol. I used to put A dot B, and then I started mistaking my dots for dots. So now I'm at pains to do a kind of roly-poly thing, just like I put arrows on top of my vectors whenever I can. So what we say is a scalar product. The vector A dotted with the vector B has a magnitude of the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay, a vector product, the vector A cross product with the vector B would give you another vector which would have a magnitude, but it is a vector of AB sine theta. So when we see a something something cosine theta, it kind of lends itself to the dot product. What are the properties? Well, the order of the vector doesn't matter. So A dotted with B is exactly the same numerical value as B dotted with A. And they are distributive. So A dotted with vector B plus vector C is the same as A dotted with B and A dotted with C added together. If they are perpendicular, because it's a cosine of the angle, then cosine of 90 is 0. So perpendicular vectors do not have a zero. It's not that they don't have one. They have a zero dot product. If they are parallel, then we don't need to worry about the angle. We just, well, the angle, cosine of the angle equals 1. So it's just the magnitude of A times the magnitude of the B. Or if they're in opposite directions, so they're parallel, but A is going in that direction and B is going in that direction. This is where they're going in the same direction. If they're in opposite directions, then we end up with a negative scalar. A scalar which is negative. If we think back about our ijk's, then an I dotted with an I is a 1 multiplied by a 1, which is a 1, and a j dotted with a j is a 1 multiplied by a 1, which is a 1, and a k dotted with a k is a 1 dotted with a 1, which is a 1, and an I dotted with a j, 90 degrees, so that's a 0, an I dotted with a k, 90 degrees, that's 0. Sorry, I dotted with a k and a j dotted with a k, 90 degrees is 0. if I have a vector, 2i plus 3j plus 4k, and another vector, 5i plus 6j plus 7k, the way I do this is I take the coefficient of the I and multiply it by the coefficient of the I, and then I add to that the coefficient of the j, add it to the multiplied by the coefficient of the j, and then I have a coefficient of the k multiplied by the coefficient of the k. And I add them up, and it equals a number. That's going to be 10 plus 18 plus 28, which is 38, 48, 56, I think that is. 56, whatever it is. It's not a vector. How many people here have done the cross product? How many people have not done the cross products? How many people are not putting their hands up? Okay. Saddest thing is when people have done both the dot product and the cross product, and they give me a cross product answer for a dot product. Because they know how to do it, but it's completely the wrong physics. So they're similar but different, so don't get them confused. Be really clear about the little stuff. Don't give points away for the little stuff. Give points away for the hard stuff, but not the little stuff. So here's a situation, a force. How do I know it's in this direction? I'm just drawing it. I'm just like saying it's in some direction, so I'm just going to draw it like that. And is used to displace a 5 kilogram mass. Let's put 5 there. And then there's my displacement, and that's going to be minus 4i plus 2j plus 4k meters. Just arbitrary vector arrows. And how much work is done? Work is equal to, it's going to be F dotted with D. Work is equal to 3i minus 6j plus 2k dotted with minus 4i plus 2j plus 4k. Work is equal to 3 times minus 4 added to minus 6 times plus 2 added to plus 2 times plus 4. Work is equal to minus 12 added to minus 12. Oh, that's interesting. Let's just double check on that. Yeah. Added to 2 4s are 8. Plus 8. So work is equal to minus 24 plus 8 is minus 16 joules. Now, what on earth does that minus 16 mean? It means you're losing energy from that object. You're taking energy away. You get a negative work when the force tends to be in one direction and the displacement is largely behind. Now it's not 180 degrees necessarily. If I'm going in this, if I'm pushing in that, but my displacement is over here, the force is kind of acting against the displacement, so it's taking energy out of the system. And you can see it, so there's my weight. And when the ball goes upwards, what happens to its speed? Its speed decreases because it's been retarded by that weight. It's got, well, actually, don't want to talk about that because actually, why don't I want to talk? That's an interesting point. I'm not going to talk about it now because I need to get on, but that's an interesting. I'm going to come back and visit that. Okay. So I'm going to skip that. So no, I'm going to ask you about this. So a 6 Newton force. Oops. A 6 Newton force points along the positive y-axis. I'm rushing, so when you rush, you tend to. 6 Newton force points along the positive y-axis, used on a 5 kilogram mass to displace the object by 3i minus 2j plus 4K.
That displaced, you just write to the side in any direction.
That's displacement direction, yeah? So it's very specific.
So you can just write in any direction?
I just drew my arrow in any direction.
Okay.
But yeah, it's very specific direction though. So, how are you going to do this? I know that work, hold on, I know that work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between. And I know that work is equal to my force vector dotted with my displacement vector. I've got an ijk, but I've not got an ijk. I've got a magnitude, and I can get a magnitude, but I don't have an angle. I could find it, I suppose, but I want to solve this problem. So which way? Who's going to? So if you're going to solve it using method A, click A. If you're going to solve it using method B, click B. Let's have a vote on this. So which is the way you're going to approach it? Are you going to approach it by trying to use our basic equation, the magnitude of the force times the magnitude of the displacement times the cosine of the angle between? Or are you going to try and solve it by using the scalar product, or sometimes called the dot product? I'm going to give you just a few more seconds because we're running out of time. I'd love to know, though. I'd love to know. Okay, I'm going to stop there. Ooh, okay. This is my feeling about it. Getting that angle is going to be a total pain. Getting that unit vector, that ijk vector, is a piece of cake. What is the ijk vector for a 6 Newton force pointing in the positive y direction? How many? Is it got an x component? Isn't it better to combine those guys together using that guy? And you know me. You know, if I'm given a choice, I'm going to see how you're going to do this. You know. Next time, we're going to talk about forces that change as the displacement happens. And we're going to look at them in terms of calculus. And you're probably going to do fine on that if your calculus is okay. We're going to look at them in terms of the area under the graph, and tradition shows that that's the question that's not answered so well. So focus on this again. We've dealt with this before. Don't give these points away. Learn how to do this skill, because it's going to come up again and again. And I will see you guys next time.